This is a coin flip simulator. And I'm going to share the link to this coin flip simulator on Canvas right alongside this link to video lecture 10. Okay, and I'll let you play with this type of coin flip simulator and extend this coin flip simulator as far out as you would like. There are buffalo nickels on the coin flip simulator. See the buffalo? Okay. How many of y'all have had prob stat at some point, whether in high school or in college? Yeah. Okay. So the probability that surrounds the flipping of a coin may not be a completely new idea to you. If it is a new idea to you, I've rigged this whole discussion so that I can be describing this stuff in very elementary terms. Okay? But I've got 4 tails up there. The buffalo is the tail. The Native American profile is the head. Okay? How likely is it if I do a flip of these coins that I'm going to get 4 heads back, or that I'm going to return to having 4 tails again? Is that something that's likely, or is that something that's unlikely? Unlikely. What's more likely to happen when I do this first flip? What type of outcome is most likely to happen? Let's see. This time we got three tails and 1 head. Okay, but if I do it again, all right, I got 3 heads and 1 tail. I'm coming back and forth. Let me check the chat real quick. 2 heads, 2 tails. There it is. There's 2 heads and 2 tails. Okay, but 3 flips in, and I've got 3 possibilities for how these coins can arrange. And none of them are all heads, and none of them are all tails. Why is that? Yeah. Yeah. 0.5 times 0.5 times 0.5 times 0.5 is really, really dad blame tiny. Not super tiny, but pretty tiny. Okay. Whereas the intermediate probabilities, I mean, it's not quite perfectly half and half, but it feels right to say, because it's a 50% chance of whether it's heads or tails, the most expected outcome would be 2 heads and 2 tails, right? Okay. What in the world does this have to do with chemistry? I'm talking like a math prof here for a bit. Well, it turns out that the coin flip story that I've got working here can be a really simple model of a mammoth set of molecules and how those molecules order themselves. Okay? The state where all the coins are one orientation represents a state of a great deal of order. Okay? It represents a great deal of organization. Whereas the state where I have half at one orientation and half other orientation represents disorder. And our chemical word that corresponds to disorder that we may have heard and we may be familiar with, what's a chemical synonym for disorder? It's in the chat. Entropy. Cool. Okay. How many of y'all dealt with entropy when you took your Gen Bio course? A little bit. You heard the word, but there weren't a whole lot of connotations to what goes into it. Okay. My best example of entropy, let me go into the whiteboard. Let me talk through a story. Okay. Here's my college dorm room. Okay. And my college dorm room was split down the middle like this. And here's my bed, and here's my desk, and here is the door to the room. And here was my roommate Frank's bed and my roommate Frank's desk. Okay? And all of Frank's stuff stayed very neatly organized on his desk. And if Frank had dirty clothes, he had a dirty clothes hamper, and the dirty clothes were all put away in the hamper. Okay? And the bed stuff that he had for his bed was very neatly organized on his bed. Okay? Frank was neat. Frank invested a great deal of energy into being neat. Well, y'all see my desk up here, right? My desk has stuff and some. Okay? And I might have a clothes hamper over here, but there's no. Okay? And dear God, my bed's got sheets and okay? And this is a very neat approximation of what my dorm room is like. And you could see the line of demarcation right down the middle of the dorm room where Frank was putting a great deal of energy into being neat, and I was not investing a lot of energy at all into not being neat, right? Okay? Frank's side of the room is low entropy. Frank's side of the room had a great deal of energy invested in the ordering of the room. My side of the room was high entropy. My side of the room had little energy investment. And there are biological examples that can correspond to this as well. A living cell is a low entropy environment. There are a lot of molecular systems organized in a living cell working in very precise fashions to get you very precise dynamic results. course, not all cells are living. Some cells deteriorate over time. And the processes that make those cells go forward stop. And the cell deteriorates. And there's nowhere near as much organization. The energy investment to maintain the order in that cell has stopped. And the cell goes into a high entropy state as a result. Okay? Of course, if I am flipping coins and I wind up with all the coins having heads, I'm probably not getting that way by chance. When I run the simulator, when I reset the simulator, all the coins go to tails, as it turns out, at each reset. There is computational energy involved in making that reset to all heads or all tails. But when I do the random flip and let chance take over, I can come up with heads, heads, tails, tails. Or I can come up with heads, tails, heads, tails. Or I can come up with, I'll just go dot, 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 many other possibilities. And the mix of possibilities of heads and tails is disordered. It turns out that the system of heads and tails in a system of 4 coins is a wonderful, simple approximation for what a real molecular system is like. And it's worthwhile to spend a little bit of time to think about how that system behaves. And it's worth a little bit of time to do computation on how this system behaves. Okay? Now, I have a brief little PowerPoint presentation I worked up this morning to introduce you to how we think about the entropy of a coin system. I wrote it up this morning to try to not screw up any of the details. But I wrote it up not to share it or provide it, but I wrote it up so that it could be something I lean upon. So I'm going to break some of my rules for how I use PowerPoints and not share this and ask you to actively take notes on this PowerPoint. Behave. Okay. Yeah. I'm going to ask you to take notes on this PowerPoint presentation real quick. Okay. And this just gets us started. Okay. If we talk about this 4 Buffalo nickel system, the state that I have up here with 2 heads and 2 tails is a state I'm going to dub a disordered state. Whereas the state that I started from, a state of all heads or a state of all tails, I'm going to consider an ordered state. And if I flip all 4 coins, I'm either transitioning from order to disorder, or I'm transitioning from disorder to order. And what I want to do with this particular set of stories here is I want to quantify how we describe the energy change, the entropy change, excuse me, in a given coin flip. Okay? And so I'm going to go through all of the different possibilities for how we flip the coin. And in all the different possibilities for how we flip the coin, I want to make sure we see the limitations on the ordered states and the possibilities and the disordered states that make us associate one with low entropy and make us associate the other with high entropy. Okay? Are we good? Okay. So, the ordered states, all heads or all tails. Now, it's very common when we do probability stuff to associate the head state with H and the tail state with T, and to declare that there is a state, H, 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 that is the ordered all head state, and there is a state, T, 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 that's all tails. Okay? Now, I'm going to assign a name to these two possibilities. They are not merely the all heads and all tails states, but they also represent single microstates. And the microstate is the core definition that I'm going to use when talking about a molecular system of this sort. And I'm talking about how I correlate the molecular system's behavior to its entropy. A microstate represents one single possibility of all of the possible configurations of a system. So not only does HHHH represent the all head state, it corresponds to a single microstate. Not only does TTTT represent the all tail state, it represents a single microstate. And like I said before, this is a really simple system we're talking about here. Okay? If we were to connect this to a real molecular system, we wouldn't be talking about, even if we're just talking about binary states, turning something on and off. We're not just talking about 4 atoms in a single system, right? We're talking about 400 billion trillion atoms in a single system. So this coin system is just a model. It's a really simple model. We're going to emphasize a little bit just how simple of a model it is. Now then, what's the difference between the state of a system and a microstate of a system? Everybody good? Let's focus on the possible states that have 3 heads and 1 tail, and the possible state that's 1 head and 3 tails. I can already tell it's too much stuff because I've got somebody shaking their hand out. Thank you for your patience with my PowerPointing. But I want to go through these possibilities. I want to make sure I've got written down the 3 head possibilities. In the 3 head state, I can have all the heads at the beginning and tails at the end, H, 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 T. are going to have the tails in the middle, HHTH, HTHH. We're going to have the tails at the beginning and all the heads at the end, THHH. There are 4 possible arrangements of the 4 flipped coins that give me 3 heads and that give me 1 tail. Within the 3-head state, there are 4 possible microstates. And from a probability perspective, 3 heads is much more likely than 4 heads or no heads because of that number of different possible microstates. And the tail for 1 head, pun not intended, the story for 1 head is just like it. 1 head can be HTTT or THTT or TTHT or TTTH. Again, the 1 head state has 4 possible microstates. And so for this 4-coin system, what I've accounted for in these first 2 slides are 10 total possible microstates. Back one real quick. Here's 1 microstate, all heads. Here's 1 microstate, all tails. Back to where we were. Here's 1, 2, 3, 4 microstates with 3 heads. 1, 2, 3, 4 microstates with 1 head. 1 plus 1 plus 4 plus 4. 10 accounted so far. We good with this? Okay. Hey, what's on the next slide? Two heads, 2 tails. And for this even split state, it turns out that I have 6 possibilities that I could be working with. Head, head, tail. Now these are much more difficult to organize. I could just have the head propagating or the tail propagating and the sea of others. These are much more difficult to organize, and so I organize them with 3 heads at the front side, HHTT, HTHT, HTTH, and then 3 with tails at the front side, THHT, THTH, TTHH. And that got me the whole complement. So for this even split, I have 6 possible microstates. And add those to the 10 I had before, that gets me 16 total microstates possible for this system. Again, real molecular systems, when we study them theoretically, have a number of possible microstates that gets into Google territory. Anybody familiar with the number, the Google, the Googol? The Google is 10 raised to the 100th power. It is a comically large number. And yet real molecular systems have that many possible microstates and many, many more. Real molecular systems are incredibly complex. We're telling a very simple story here that allows us to focus on a very simple set of probabilities. Okay? One possible microstate out of 16 possible can be all heads. One possible microstate out of 16 can be all tails. I have 4 possible microstates out of the 16 with 3 heads. I have 4 possible microstates out of the 16 with 1 head. Oh, 4/16, that simplifies as a fraction to 1/4. And therefore those probabilities. I have 6 possible microstates out of the 16 that have 2 heads. 6 over 16 simplifies as a fraction to 3/8. And so I can go back to my coin flip simulation and just start flipping over and over again. And see as I flip how the individuals come out. And I would expect 6 out of every 16 to turn up with 2. I'd expect 4 out of every 16 to turn up 1 and 3. I'd expect 1 out of every 16 to turn up 0 and 4. Now, 10 flips is an awfully small survey of this. Blessedly, we have the 10 flips button sitting down here, and I can just simulate 10 flips at a time instead of 1 flip at a time. I'd expect 6 out of 16 or 60 out of 160 to be 2. I've got 66. I expect 4 out of 16 or 40 out of 60 to be 1 or 3. I've got the 1 dead on here. The 3 seems to be not happening a whole lot. And I expect 1 out of 16 or 10 out of 160 to be 0 and 4. I'm getting that a little bit more often than I think is proper. In fact, I've got 4 tails turned up here right now. Now, this is how you know you have a real theory and math nerd sitting up here in front of you. He just goes, I wonder how good the data would be if I got to 1600 flips. So I'm just going to start flipping. Flip them all. Flip all the coins. Halfway there. The single takeaway I want you to take from this scenario is Pearson is a mammoth nerd. 1600, woot. This should be 600 of the 1600. I'm pretty close. Hey, I'm still bang on 400 of the 1600 here. This got darn near to 400 of the 1600. I'm about at 100 of the 1600 here. I'm a little bit shy of 100 of the 1600 here. I'd get even closer if I went to 16,000. Do you think I'm crazy enough to go to 16,000 in front of you? No, that would take too long. I'm not going to do that. But you certainly could. And as you gather more and more of these simulations, you find these probabilities fall more and more into place, and they're more and more true. Real molecular simulations go through these comically large 10 to the 100th power of microstates, some of them several thousands and millions of times every second. Real thermodynamics is incredibly complex. Okay? Now, my big goal going through this was to represent these microstates with entropies and to make them numerical. So let's talk about what goes into these transitions. First, the transition we don't expect. Having a possibility where I've got two heads and two tails and flipping those coins and having those coins come up all heads. How likely is it from any position that I flip 4 coins and have all 4 coins come up heads? Well, that would be 1/16 of the time, like I just saw. Not terribly often. And a transition that takes me from a state where I have a maximum of microstates possible to a state where I only have the one microstate possible is a transition from a disordered state to an ordered state. It's a transition that decreases entropy. Let's go to the flip side. The flip side, pun not intended, I swear. The type of story that I did at the very, very start of this. Where I started with all tails. And I did a flip. And I came up with 2 heads. Is that the exact flip that I described in the slide? No, it's the opposite of the flip. I got TTHH instead of HHTT. But it was the 2-head state. And I just brought that up on the slide and clicked it because I expected that outcome. I expected to go from all tails to 2 heads. That won't always happen, but it will happen at least a strong plurality of the time. That's a transition from an ordered state to a disordered state. That transition increases entropy. Okay? So this is a transition describing an increase of entropy going from one possible microstate to 6 overall microstates. That's an increase in entropy. A transition where I go from 6 microstates to 1 microstate is a decrease in entropy. And the fun question immediately becomes, well, how big of an increase or how big of a decrease in entropy is it? Okay? And before I bring up the slide that actually has the equation on it, I'm going to go to the whiteboard and I'm going to doodle out the equation, and I'm going to give the equation a quick application. Okay. Everybody good on this slide? Okay. To the whiteboard with me. The way we quantify the concept of entropy is we owe it to a person in the late 1800s who studied a discipline known as statistical mechanics, taking molecular systems and connecting them with the type of statistics we're talking about here. Okay, his name was Ludwig Boltzmann. And literally, this equation was so important to him that it's found on his tombstone. I always wanted to have an equation like that. S is the symbol for entropy. The absolute entropy of a molecular system is equal to a constant times the natural log of the number of microstates. So W for my two-head state in the four-coin system would be 6, because there are 6 possible microstates associated with the two-head state. For the one-head or three-head states, W would be 4. And as we'll go through in a bit, for the no-head or four-head state, W would be 1. The B in case of B stands for Boltzmann. Case of B is Boltzmann's constant. Boltzmann's constant is tiny. Its order of magnitude is the inverse of the order of magnitude of the mole. Its value is 1.381 times 10 to the negative 23rd. And its units are joules per Kelvin. I'll talk about why the units are joules per Kelvin when we get into class on Tuesday of next week. Okay? So, let me talk about the four-head state. There's only one possible microstate for the four-head state. And so the absolute entropy of the four-head state is equal to 1.381 times 10 to the negative 23rd joule per Kelvin times the natural log of 1. Okay, pre-calculus people, what's the natural log of 1? Anybody up for the natural log of 1 in the chat? Don't feel like you have to be. If you want to be, I can't see you in the chat, so just go ahead and take your calculator and push in the natural log of 1 into your calculator and see what comes out.
Is it 0?
It is so 0. The natural log of 1 is very, very 0. And so that constant doesn't matter. And the absolute entropy for a single possible microstate is 0. We consider a single microstate to be perfectly ordered. Okay? Even in real molecular systems, with all the possible microstates in all the possible orientations, perfectly ordered doesn't happen. Entropies of 0 don't happen. We have a name ascribed to an absolute entropy of 0 being achieved in the universe. It's called the heat death of, or I just about botched thermodynamics. And absolute entropy of 0 would be a perfect crystal. It would be the opposite of the heat death of the universe, as it turns out. It would be a death of the universe that required everything to become perfectly ordered and everything to stop moving because of perfect order. That type of ordering does not happen. Okay? And we'll be able to go into our standard thermodynamic data and have an example of this as it turns out. Okay? Now, I don't just want to describe an absolute entropy, though. I want to describe an entropy change. So let me take 2 other states of this system. Let me describe a transition from the 1-head state to the 2-head state. And let's just go ahead and remind ourselves of the possibilities that we had when we just had the 1 head. And then let us remind ourselves of the range of possibilities that we had when we had 2 heads. I have to remind ourselves of the range of possibilities we had. It takes me a moment to remember. Now, the actual flip of the coin can start from any one of these states and go to any different one of these states. But because there are 4 microstates associated with 1 head, and because there are 6, let me see if I can do this real quick in here, 6 microstates, yeah, it works, associated with 2 heads, I still consider a flip that takes me from any single one-head scenario to any single two-head scenario to associate with an increase of entropy. And I still study the number of microstates initially and the number of microstates finally. And I can still stake out an initial entropy of K sub B times natural log of W initial. I don't know why I try to put a ln there. And a final entropy equal to K sub B times natural log of W final. And let me just number crunch this out. The absolute entropy of the initial state is 1.381 times 10 to the minus 23rd joules per Kelvin times the natural log of 4. Now, I'll always do these on my calculator in front of you. So you can either just trust my calculations or you can follow along on your calculator yourself to come up with these calculations. And following along on your calculator means you're finding where the natural log is on your calculator. That turns out to be 1.915 times 10 to the minus 23 joules per Kelvin. Again, this is a really tiny entropy, but it's a really tiny entropy because it's a really simple molecular system. Okay? Let me do the same number crunch for the other side. (1.381) times 10 to the minus 23rd joules per Kelvin times the natural log of 6. (1.381) times 10 to the negative 23rd times the natural log of 6. That'll get me 2.474 times 10 to the minus 23rd joules per Kelvin. And so I've got an initial entropy and I've got a final entropy. What I can talk about in this transition between systems is a change in entropy, delta S. And every time I do a delta in thermodynamic stuff, I'm doing what minus what? Final minus initial. Final entropy minus initial entropy in this story. So 2.474 times 10 to the minus 23rd joules per Kelvin minus 1.915 times 10 to the minus 23rd joules per Kelvin. (1.915 E minus 23 joules per Kelvin. And that gets me 5.59 times 10 to the minus 23rd joules per Kelvin. 24th, excuse me. 2.474 minus 1.915 is 0.559. I need to transition this guy right here from minus 23rd to minus 24th. Hey, that's a lot. And it's a lot with really tiny numbers that are really not realistically large at all. But it still says something useful. The useful thing that it says is that when I transition from a lower entropy state to a higher entropy state, I must be increasing in entropy. And I'd like to have something that quantifies that increase in entropy. And this relationship does that. Now, it would be nice if I didn't have to do quite as much number crunching. There's one principle of logarithms I can bring to bear that can help simplify the number crunching for when I need to do delta S. And let me talk through that real quick here. And this is one example that we won't apply that much here, but we're going to see other examples of this as we go through and encounter more logarithms in what we study later on as we start to talk about equilibrium. Now, first way I can simplify this. I can totally factor K sub B out, right? So writing this general relationship for delta S is the same thing as writing K sub B times the natural log of W final minus the natural log of W initial. It turns out that there's a property of natural logarithms and other logarithms where if you subtract one logarithm from another logarithm, it's the exact same mathematical function as taking the logarithm of the first divided by the second. In other words, the natural log of W final minus the natural log of W initial is the same thing as the natural log of W final over W initial. Now, it turns out I've just done a delta S computation for one example up here. For a W of 6 is final and a W of 4 is initial. So let me try that and let me see if it works in the same way. Let me take 6 divided by 4. Oh yeah, 6 divided by 4 is 1/2. And let me take the natural log of 1/2, 1 1/2, excuse me. And oh, that's 0.4055. And let me multiply that by Boltzmann's constant, 1.381 E minus 23. And that gets me out to 4 significant figures. The exact same thing. If you've taken notes with me through this, and you haven't had your calculator by your side doing the number crunching, I really encourage you to go through these 2 calculations and demonstrate for yourself that these 2 calculations are identical to one another. Doing this type of computational demonstration will really help you gain an instinct for how you are tackling the problem types that come up associated with this. Okay? That's me going through all of the mathematics. Okay? Part of the reason that this mathematics is useful is because it tells us where increases and decreases in entropy come from in molecular systems. From the increasing sophistication in the 2 heads, as opposed to the increasing order in all heads or all tails. Okay? But again, when we talk about the total number of microstates accessible to us being on the order of 10 to the 100th power, real computations of this sort, I mean, this calculator only goes up to 9.99 times 10 to the 99th power. I have real limits to how I can actually handle computations on this thing. There's an example in the homework of a really complex coin system that shows you how difficult it is to get up to the types of entropy changes that get us to 1 joule per Kelvin of difference. It's really difficult. Okay. But let me talk through a real system with a real number of microstates on a molecular level real quick before we go. Take that equation and explain it in words. What type of transition am I talking about here? I'm taking carbon from the solid phase in graphite, the same type of stuff that turns up in pencil. And I'm transitioning it to a gas. Okay? Let me spoil the story before I tell it. How likely is it in our normal day-to-day existence that we see carbon go from solid graphite to the way some of y'all have been taking notes, you might be feeling like the pencil lead and your pencils get vaporizing as you go through and do this. But it still is going onto the paper. It's still giving you marks on the paper. It's still in the solid phase. Okay. Not likely that we see that solid phase writing on the paper suddenly vaporize and go into nothing, right? Let's look at data from our thermodynamic data table for this particular transition. From our thermodynamic data, there we go. Now, this is the part of the table I've been concerned about up to this point when I'm talking about carbon. I've been concerned about this column right here, talking about carbon's enthalpy of formation, which is 0 for graphite because that's the standard state, which is small but still substantial for the transition to solid in graphite form, in diamond form, excuse me. But which is really, really mammoth for the transition from solid and graphite form to the gas. Okay? And I can take this statement from my table and I can write down on my table what the enthalpy of formation for this is. That really, really mammoth enthalpy of formation for carbon in its gas phase is why we don't tend to see carbon take a transition from solid phase to gas phase, because it takes a lot of energy, even more energy than those of you writing notes this morning have been putting in. It takes a lot of energy to vaporize graphite. But there is a reason why vaporized graphite should emerge. And that reason is found in the last column of our thermodynamic data table. The column labeled standard entropies. Now, remember what I said before about a standard entropy of 0. An absolute entropy of 0 represents a perfectly crystalline, a perfectly ordered substance. And oh, in this particular list over here is the most perfectly crystalline stuff that you know. Because you can tell the difference between carbon that's in your pencil lead and carbon that's on jewelry, right? And that very distinct sparkle and shimmer of diamond is associated with that very ordered crystal. This is as low as entropies go in our tabulation, the entropy of diamond. But that entropy is still 2.4 joules per Kelvin per mole. Not times 10 to the minus 23rd. There's still a lot of microstates associated with carbon in the diamond phase. It gets us entropies that are so much higher than our entropies were for our coin flipping system. And carbon in the graphite is more than double that entropy, but it still is a relatively low entropy. Okay, 5.7 joules per Kelvin per mole of carbon. But on the other hand, the entropy of carbon in the gas phase is really substantial. And if I'm going to write out what delta S looks like for this reaction, I'm going to put a standard symbol because this is coming from the standard entropies. That's going to be equal to the standard entropy of my product, carbon in the gas phase, minus the standard entropy of my reactant, carbon in the graphite phase. Okay? And in that tabulation, the entropy of carbon in the gas phase was 158.1 joules per mole per Kelvin, minus 5.7 joules per mole per Kelvin. That distinction, 158.1 minus 5.7, 152.4 joules per mole per Kelvin. The transition of any stuff from its solid phase to its gaseous phase is a transition that's entropically favored. I got one other example of this type of transition that we know happens well. What happens if you leave a glass of water sitting out for a very long time? It evaporates, absolutely. That's something that happens naturally. That's something that happens with spontaneity. Like we said, we know that solid carbon doesn't go to graphite with spontaneity. And we know that because this number right here tells us that energy must be input to vaporize carbon. But what this example does is it sets up the next phase of chemistry we need to understand. What this example does is it tells us that there is a balance here between the entropy change that is favored for the vaporization of carbon and the energy input required to make it happen. And there are similar numbers I can compute for the energy required to vaporize water and the entropy change I get out of that. Water naturally vaporizes. Water's vaporization is spontaneous. Carbon's vaporization most certainly is not. Why the difference? The next phase of this course is about answering why the difference. The thing I haven't described well at all as we've gone through today's business is what in the world this joules per mole per Kelvin represents. And when I very first gave the units of Boltzmann's constant, joules per Kelvin, I said, I haven't told you where these units come from. I'm just giving this to you right now. I need to tell you where those units come from. And we'll do that on Thursday as we go from talking about these microscopic changes to talking about these changes macroscopically. Heat transfer is involved. See y'all on Tuesday. Watch your email for news about the assessment.